Alright, in this video here we're going to talk about the multiplicity of a zero of a polynomial function. Right? So remember what a zero is, and if you haven't watched the video that I did about zeros of a polynomial, you should check that out. But just real briefly, what a zero is a number that when you plug it into the polynomial function, it equals zero. The whole function equals zero. Another way to think about it graphically is the zeros of the function are the x-intercepts of the graph. Right? So we're going to talk about the behavior of the graph as it is near those different x-intercepts depending on the multiplicity of the zero. Now what we mean by multiplicity is how many times the factor appears in the polynomial, right? So if you write the polynomial in a factored form, sometimes factors appear more than once, right? So if our multiplicity is 1, that means the factor is only there one time. If our multiplicity is an even number, that means that factor is there 2 times or 4 times or 6 times or some even number of times. And if our multiplicity is an odd number greater than 1, that means our multiplicity is like 3 or 5 or some other odd number that's bigger than 1. That's how many times that factor would be there, 3 times or 5 times or so on. Right? So depending on what the multiplicity looks like, the graph does something different when it hits that x-intercept, right? There's 3 different ways the graph can behave when it hits an x-intercept, when we're talking about polynomial functions, right? So for those 3 different multiplicities, here's the shape of the graph near that x-intercept. So first off, when a multiplicity of 1, so if a factor only appears in our polynomial one single time, the zero that we get from that factor, which gives us that x-intercept, the graph is just going to go straight through that x-intercept. Just like a linear function, it's like a straight line. When it hits an x-intercept, it just goes straight through. Same deal here. Now, it can go in either direction. It can go, from the bottom up, or it can go this way, going down. I only had enough room here to really draw one of those, but it could have either orientation. It could go straight through on the way down, or straight through on the way up. Right? So if your multiplicity is 1, if that factor is there, like to the first power, only there one time, then when it hits that x-intercept, it behaves like a linear function, just a line going straight through. All right. If our multiplicity is even, right, so that factor is there 2 times or 4 times, it has an exponent of 2 or an exponent of 4, well then it behaves like a quadratic function. And if you remember what the graph of a quadratic function is like a parabola, that means that when that graph hits that x-intercept, it bounces off the x-axis, right? So it doesn't actually go through the x-axis, it hits the x-axis and bounces off the other way, just like the graph of the quadratic function, y equals x squared, hits the origin and then bounces back the other way. Same deal here. All right, so like I've said with a lot of other videos that I've done, if you can relate the things that you're learning to things that you already know, it makes it a lot easier to understand what's going on. And that's what I'm trying to do here, right? When the multiplicity is 1, it behaves like a linear function. It just goes straight through like a straight line, right? When the multiplicity is 2 or 4, it's an even multiplicity, well, then it behaves like an x to the second or an x to the 4th power, like a quadratic function, and it bounces off the x-intercept. Right? And once again, it can go either way. It can come from the bottom and hit the x-intercept and bounce back down, or the way I have it drawn here. Right? There's 2 different ways that could go. But no matter which direction it's going, if you have an even multiplicity, it bounces off that x-intercept. Right? The graph hits the x-axis and then goes back the other way. It doesn't actually go through. And then the last multiplicity we have is if we have an odd multiplicity bigger than 1. Right? If the multiplicity is 1, 1 is an odd number, but that's like an exception. That's when it behaves like a line, like an x to the 1st power, and just goes straight through. If I have an if I have a multiplicity of 3 or 5, where that factor is there 3 times or 5 times, it's being raised to the 3rd power or the 5th power, well then it behaves kind of like a cubic function, an x to the 3rd power. If you remember what the graph of x to the 3rd power looks like, it comes up through the 3rd quadrant. As it approaches the origin at 0, 0, it kind of curves as it goes through, and then it continues up on the other side. Well, when I have a polynomial with a 0 that has an odd multiplicity bigger than 1, when it hits that x-intercept, it behaves just like that cubic function. It curves as it goes through the x-intercept. It doesn't just go straight through from one side to the other. It does that little wobbly curve thing as it hits that x-intercept, right? And again, just like the graph of a cubic function, right? So if you can relate these rules back to hopefully what you already know about the graph of a linear function, the graph of a quadratic function, the graph of the cubic function, the behavior of the graphs near those x-intercepts look a lot like the graphs of those functions, right? This looks just like a cubic function. This looks just like a quadratic function. This looks like a linear function. This looks like a quadratic, and this looks like a cubic function, right? And the cubic function, just like the other ones, it could go the other way as well. It could come down from the top and then curve through and continue going down, All right. So those are the multiplicities, the rules for the multiplicity, what the graph looks like when you hit each of those x-intercepts. All right. So what I'm going to do now is pause the recording and erase this stuff, and we'll actually take a look at a polynomial, and we'll look at the multiplicities of the zeros, and then what the graph will look like as we hit each of those x-intercepts on the graph. All right, so I put up an example of a polynomial function here. P of x equals x to the fourth power times x minus 2 to the third power times x plus 1. All right, so this polynomial is already in the factored form for us, which is nice because if we were to actually multiply all this stuff out, to try to factor that from there would be probably a pretty difficult thing to do. So for a lot of these problems where you're dealing with the multiplicities of the zeros, a lot of times it's already given to you in the factored form, so you don't have to worry about actually doing all that factoring yourself, which, like I said, would be a really difficult thing to do. If you can imagine what this would look like if we actually did this x minus 2 to the third power and then multiplied it by this and then multiplied everything by x to the fourth, that would be a nightmare to try to factor. Right? But this is the factored form. So since we have this in the factored form, first thing I need to do is find my zeros. Remember, the zeros of a polynomial, and again, if you didn't watch the video I did about zeros, you might want to check that out because that's what we're doing here. To find the zeros, or to find the x-intercepts of the graph, I set my whole function equal to 0, and then I'll separate each of my factors and solve each one. All right, so I have 0 equals x to the fourth times x minus 2 to the third times x plus 1. It already has these three factors, so let me just do each one individually. So 0 equals x to the fourth. I have 0 equals x minus 2 to the third power, and I have 0 equals x plus 1. Right, and now I need to solve each of those for x. Well, for this one, for x to the fourth power equals 0, a couple ways to think about it. You can think, well, how do I get from x to the fourth down to just x? And the answer would be to take the fourth root on both sides of the equation. And the fourth root of 0 is just going to be 0. So this is going to give us x equals 0 as one of our x-intercepts of our graph, one of our zeros of the function. Right, another way to think about it is, well, what number raised to the fourth power equals 0? The only number raised to a power that equals 0 is going to be 0. Right, so that one should be hopefully pretty obvious that that's what that one is equal to. All right, so this is x equals 0 with a multiplicity of 4. Right, because that factor of x was in there 4 times. Right, so the 0 itself comes from getting the factor, setting it equal to 0, and solving. The multiplicity comes from the exponent that's on that factor. So this x was raised to the fourth power, so x equals 0 has a multiplicity of 4. All right, for the next one, 0 equals x minus 2 to the third power. And when we have something raised to a power equal to 0, it's just about like we can ignore the exponent. Right? I could take the third root on both sides of the equation to cancel out that third power, and the third root of 0 just equals 0. Right? So I get 0 equals x minus 2, and then when I add 2 to the other side, I get x equals 2. Right? 2 is the number that I would plug in here to make this whole thing equal 0 to the third power, which equals 0. Right? So x equals 2 has a multiplicity of 3. Right? And again, that multiplicity comes from the exponent. That factor of x minus 2 was in my equation 3 times. Right? So it has a multiplicity of 3. Right? The factor of x was in that equation 4 times, so that one has a multiplicity of 4. Right? The 0 equals x plus 1, well there, if I just subtract the 1 to the other side, I get x equals negative 1. Right? And the negative 1 has a multiplicity of 1. Right? Because up here, right, this x plus 1 is just raised to the first power. Right? X plus 1, there's only one of those factors there, so that one has a multiplicity just of 1. All right, so this particular polynomial function has 3 different zeros, right? Negative 1, 2, and 0, and each one has a different multiplicity. All right, so that's what we mean by the multiplicity of the 0. That factor of x minus 2, how many times is it in there? Well, since it's raised to the third power, that means that that factor is actually there 3 times. All right, that x, since it's raised to the fourth power, that means that it's there 4 times, so it's multiplicity 4. The x plus 1 is to the first power, so it has a multiplicity of 1. All right, so those are our zeros and our multiplicities. So then what this means if I actually try to sketch a graph of this function. All right, so I'm just looking at the numbers I have here to make sure I label enough. So here's negative 1, 0, and 2. All right, so those are where I'm going to have my x-intercept. So I'm going to have an x-intercept at 0, at -1 and also at 2. I said 0 and then I put it at -1. That's kind of weird. But I have an x-intercept at -1, 0, and 2. Right? Those are the values I got for my zeros of the function, which are the x-intercepts. And now I have to talk about, well, what is the behavior going to look like when I hit each of these x-intercepts? Now, to get an idea of what this graph looks like, I'm going to refer to the end behavior of the graph, which if you did not watch the video that I did on end behavior, you should, because that ties into graphing a polynomial. But I'm not going to really talk about it much here. I'm just going to figure it out and put it up here. It's going to be a 4, 3, 7, 8. So if I were to multiply this entire function out, I have an x to the 4th times an x to the 3rd times an x to the 1st power. If I add all those up, I'm going to get an x to the 8th power, and I'm going to have a positive leading coefficient because there's a positive x to the 4th, a positive x to the 3rd, and a positive x to the 1st. So a positive x to the 8th means my end behavior is both sides going up. Right? If you have no idea what I was just talking about there, go back and watch the video that I did on end behavior where I explain how you can figure out the end behavior of a graph and which direction it goes on either end. But I just kind of real quick did that just so I know what this graph is going to look like. But the main focus here is the x-intercepts and what's going on there. Right? So at x equals -1, right? So my graph is going to be coming down from above. The first x-intercept it's going to hit is -1, and that has a multiplicity of 1. Right? So remember, a multiplicity of 1 means it behaves like a linear function, an x to the 1st power. It's just going to go straight through the x-intercept. All right, so at x equals 1, or at x equals -1, since the multiplicity is 1, right, I can write this over here, it's just going to go straight through. All right, straight through that x-intercept at -1. Again, it's like an x to the 1st power. It's a linear function. Just goes straight through. My next x-intercept is at 0, and that has a multiplicity of 4. So remember, if I have an even multiplicity, that means it behaves like a quadratic function. It's going to bounce off that x-intercept. Right? Since 4 is an even number, somehow this graph is going to turn around down here and come back up to this x-intercept at 0, but it's going to bounce and go back down again. Right? So even multiplicity, it behaves like a quadratic function. When it hits that x-intercept, it bounces back down in the other direction. Right? And then my last x-intercept at x equals 2, which has a multiplicity of 3. Remember, when there's a multiplicity of 3, it behaves like a cubic function, which curves as it goes through its x-intercept. Right? So multiplicity of 3 means it curves through the x-intercept. Right? So once again, this is going to come down a little bit, come back up, and then curve as it goes through x equals 2. Right? Now, the parts about graphing the polynomial that we don't know about are these parts down here. I don't know exactly how far this is going to go down before it turns around and comes back. I don't know how far this one goes before it turns around and comes back. To get accurate information about that, those local minimum or local maximum points, you need to know some calculus in order to be able to pinpoint exactly where those points are. Right? But once you learn a little bit of calculus, and this is something you learn in a Calculus 1 class, you can figure out exactly where that local or relative minimum point is, exactly where that local minimum point is. And then with all this other stuff we're doing here with the polynomials, you can have a better picture of what this graph looks like. Right? But our focus here is on the zeros. So yeah, to get my zeros, I set my polynomial function equal to 0. It was already factored, so I separate my factors, solve each one. The exponent that I have on each factor gives me my multiplicity. Right? And the multiplicity tells me how the graph behaves. Multiplicity of 1, it behaves like an x to the 1st power. It goes straight through that x-intercept, look, just like it's a straight line. Right? Multiplicity of 4, any even multiplicity of 2, 4, 6, or so on, bounces off the x-intercept. So it comes back to x equals 0, bounces back down. X equals 2 has a multiplicity of 3. Any odd multiplicity that's bigger than 1 behaves like the cubic function, where it curves as it goes through that x-intercept. And there we have a picture of the graph of this polynomial function up here. Right, so that's multiplicity of zeros. Make sure you check out the other videos I've done on polynomials, the one I did on end behavior, which I kind of mentioned here, the other one where I talked about the zeros. And I'm going to do another one now where I talk about just some general guidelines for actually graphing a polynomial and kind of putting all that stuff together to actually draw one of these graphs pretty accurately.